In the interaction between KVM and the Linux kernel, and especially in the interaction between the KVM memory management and the Linux kernel memory management. I work for Red Hat. And so I'm going to talk about the next things which I think will happen in the memory management of Linux for KVM, specifically for KVM. So the first thing is the alignment we need in QEMU and QEMU KVM to get full advantage of transparent huge pages. So transparent huge pages was my last project, which got merged into the upstream kernel recently. And we still miss a little patch to do the right alignments for the guest physical memory in the QEMU virtual address space. And without that, the page tables in the Linux host will be 2 megabytes, huge. But the shadow page tables built by KVM will not, unless you get the right alignment once every 512 times you run it. So we need this little patch. I posted it some time ago, need to do it again, and I just want to raise the attention because this is quite important. I'm pretty sure there have been benchmarks done without this little patch, which practically could have been better if this was already applied in QEMU upstream. Of course, RHEL 6.2 has the patch. All the RHEL 6 have the patch, but we need it in the QEMU upstream. And then there is MRMAP optimization, which is probably one of the last optimization I'm doing for transparent huge pages upstream. It's boosting THP and not THP use. And as usual, the speed up is more significant in the guest. Often, transparent huge pages helps more when you use virt rather than using only bare metal and Linux on the host. So this was actually the patch we need to merge. I'm not sure how you want to implement it, but this must be done. And it's actually not only my task, but the task of the QEMU community to do this little thing. It's really simple, and we need to do 4 megabyte alignments for 32-bit builds of QEMU, and 2 megabyte alignment for 64-bit. And this is actually the improvement I got out of MRMAP. I think this could boost spec JVB a lot in the guest. And MRMAP gets so much faster when it's actually moving huge pages with a huge PMD natively without splitting anything. So this is the improvement with transparent huge pages off, which is also improved because I'm removing a lot of IPs during the MRMAP. So I optimize the MRMAP even if you're not using huge pages, transparent huge pages. And this is actually the same result with transparent huge pages upstream and without transparent huge pages upstream. So you can see there's quite some huge boosts here. So going in some other topic, more interesting for KVM than MRMAP. There is some work from Michel Lespinasse from Google on some working set estimation code. And the patches have been posted on LinuxMM. There is some trouble with get pages unless 0 in the implementation that we are working out. But still the point is we could use this work of working set estimation to improve the ballooning. So they need to estimate the working set of a certain workload in a C group to set a soft limit for the C group. Soft limit is not an hard limit where you actually run out of memory. It's more a soft limit where even if you exceed it, you are still not running out of memory. So it's just trying to get the right cache levels and optimize for the right C group sets. But we could use this information to drive the ballooning driver in some auto-ballooning mode. And the ballooning driver has also an additional optimization required for transparent huge pages because it should send 2 megabyte guest physically contiguous regions back down to the host when the balloon is inflated. Right now it's sending 4K pages. It's not taking much care if the guest memory is virtually contiguous or not. It needs to be improved, because if we do that, we can use compaction in the guest to generate these 2 megabyte pages, and we can allocate and free native 2 megabyte pages in the balloon driver. That should improve the ballooning driver performance. Recently, there have been other patches in KSM. KSM is working very well, and many people is using it. And this new feature basically tries to use the DLT bit in the page table and in the shadow page table for those implementations which have it, like NPT, for tracking which pages are frequently changing. Because if a page is frequently changing, we don't want to merge it with KSM, because if it changes frequently, if we merge it, it will be copy on write, and it will be broken basically again very soon. We only want to merge with KSM those pages which are not changing, which are mostly read-only. And this dirty bit would avoid some overhead in the current implementation. On the other end, to clear the dirty bit, we need to send an IP to the guest to flash the dirty bit from the shadow page tables. So it's actually going to slow down the guest bit, but it will make, you know, a faster KSM scanning. So I'm not sure if it's the best thing to do, but it's definitely something which might happen in the future, to have an option to use KSM through dirty bit to find these frequently changing pages which we don't want to deal with in KSM. So changing topic again, and this is the big thing for this presentation is NUMA. So, you know, NUMA exists in Linux for 10 years. We had so many features for NUMA. And I always like to work on things which, you know, are more, they have more user base. And recently, I even got a NUMA machine at home. So I think NUMA is really getting mainstream. And the current Linux kernel has a lot of functionality called memory policy, scheduler affinity. We have so many NUMA heuristics and tricks, but they are always mandated from userland. So you need to make the application NUMA aware. And, or you need to use bindings external to the application. You have to run the application with some wrapper which pins the application to this node of the NUMA system. So I started working on something which might be a little more automatic, which I usually call Autonuma. And it's not completely defined yet. I only have a proof of concept and some benchmarks on it. But I just want to show that some of these pins that you have to use today to get good performance on a NUMA machine are not actually necessary. We can have more intelligence in the kernel and leverage the fact that the application, including QEMU and KVM, of course, is running on Linux on virtual memory to actually move the memory in the right places and move the vCPUs in the right physical CPUs. So as usual, like with transparent huge pages, I'm improving, you know, Linux, but I do it for KVM. And the end result, of course, works for everything else too. So it's not really specific, but for KVM it's very important, because KVM is a long-lived application. So you can start it, and it keeps running 1 month as long as the process is the VM keeps running. While for many other applications, the current heuristics we have in the scheduler of Linux, they are pretty good. Like if you run a GCC compilation, each GCC task won't take more than a couple of seconds at most. So the current heuristics in Linux to deal with NUMA are pretty good for short-lived tasks like GCC, but definitely bad for long-lived tasks, incidentally, like QEMU and KVM. So I'm going to show you a little bit what happens today with the current Linux scheduler and with the current memory management in Linux when you deal with the NUMA system, just like mine. Mine is 2 nodes. There are 2 sockets. And you may have a KVM started on CPU 0. And CPU 0 belongs to node 0, which has some attached RAM, RAM 0. And you might start allocating memory because KVM starts running and it's touching the memory. And the default memory policy in Linux allocates memory from the node of the CPU which is running on. So the process is running in CPU 0, and it will allocate memory from RAM 0. This is the preference in the default memory policy. So the memory will go here, which is perfect. We have local memory, and that's what we want. What's the problem? The problem is you may have some workload. I made an example of make -j. Actually, it should be lowercase, but who cares? But the point is you may have some overwork in the host for whatever reason. Maybe you have Python scripts running for some SCSI device, which is doing some distributed SCSI. And this overwork, for whatever reason, moves the KVM task in node 1, so to the CPU 1, which belongs to node 1. And I have to say the current scheduler is pretty sticky. It's really not moving tasks around so much. So this is not so common to happen, but if you have an application running for 1 month, it will definitely happen. I mean, eventually it will just go in the wrong place. And what happens then? After the make-j workload goes away, then the KVM task from the CPU1 will keep accessing the memory in RAM 0. And that's it. I mean, there is no knowledge in Linux which can fix things after the fact. So after that, the KVM task, as far as the Linux scheduler is concerned, might keep running in CPU1 forever. And it might always go to the wrong node in the memory accesses. And of course, that's slow. So the previous configuration was fast access because it's local memory. This is slow. And it might stay there for a long while. And the problem is the current scheduler is completely memory blind. So of course, we can actually do bindings and prevent this to happen, so the KVM task never gets scheduled. But you know, when we deal with virtual machines can be started, they can be migrated, they can allocate more or less memory, and it's pretty hard to make a static binding for the administrator. If there are other virtual machines coming in anytime, you may have CPU overcommit. So if things are figured out by the kernel, it's kind of much simpler for the administrator to deal with these problems of NUMA optimizations. So what we have today are NUMA bindings, and I'm just showing you what's available. And some of these are pretty handy to use, like /dev/CPU sets. And the rest are syscalls. So you can use syscalls to do bindings and limit the process to a certain node in terms of allocation and CPU. And you also have the full topology of the system in /sys. So you could actually change your application to parse the NUMA topology in the hardware and try to call these syscalls with right numbers. But of course, I'm not sure how many people are really going to do that for normal applications. If you have a supercomputer, you're forced to do that. Otherwise, you will get horrible performance. And the supercomputer is very expensive. The developer time is still expensive, but probably not as much as the computer. But if you have normal application running on normal hardware and normal NUMA systems, changing everything to do these things is kind of time consuming and not so easy too. So in my example, my system has 24 threads with hyperthreading, 12 cores, and 2 sockets. And this is the topology of the system, and this is how it's represented by the Linux scheduler domains. The Linux scheduler has an internal implementation called scheduler domains, scheduler groups, and that's how it represents it. And from 0 to 17, you have physical cores, And from 0 to 11, you have physical cores. To 12 to 23, you have the threads from hyperthreading. So of course, it looks weird that here in the first node we have 0, 12, and 1, 13, but that's because of the hyperthreading numbering. The point is you have these CPUs in RAM 0 and the other CPUs in RAM 1. And you can actually make the application to make static bindings to these CPUs, but you really have to call the syscalls with these numbers. And you have to build these numbers from the sys file system. And that's, as I said, is kind of tricky. And a job manager can also use some functionality and call back from the CPU sets file system. And it can also do its own heuristics. And it's probably not as efficient to tell which CPUs are idle and which memory is important for each process and thread. So even if you can actually do static bindings, it's pretty hard for these systems we have today, the one I showed before, to tell which are actually the VM which are more idle and with the VM which are more under CPU load. So it's pretty hard to deal, for example, with CPU overcommit. If you have a CPU which is idle, you don't care even if it's allocated in the wrong node. If it's not running often, you care much more about those CPUs which are very high CPU utilization, not much about the idle ones. So it's pretty hard with the hard bindings to optimize the whole cloud node, in my opinion. And I just wanted to also have an estimation of how bad really is not to deal with NUMA. So basically to have the VM running on remote memory, so the worst case. And I wanted to see the difference as well with running with static bindings and with some new Autonuma algorithm I wrote. So I'm going to show some benchmark. And all of these benchmark will still have one binding for the memory. So I'm not yet migrating memory around automatically. I'm allocating memory statically, which each process has its own static memory. But then I compare what happens in the scheduler. So this will be the first kind of benchmark, which is basically using bindings for everything. And it's actually the best binding you can do. So you have a parent process with n threads, could be 1 thread, 12 threads, or 24 threads. It's 3 different benchmarks. And this parent process allocates memory with memory binding to the node 0. The memory binding for the memory will be constant for all the benchmarks. So I'm not moving memory. I'm allocating memory in the optimal way. And in this kind of benchmark, we also have a set affinity binding where the CPUs are also binding the optimal way. In the second benchmark, we have a set affinity remote, which is actually the worst possible configuration you can have in a NUMA machine, where you have all the memory which is remote for the CPU. So the parent process here has the memory allocated in RAM 1, but the CPUs are connected to node 0, not node 1. So basically, you always run on remote memory. And then I just removed the set affinity bindings, so you only have, basically the scheduler is free to run as it wants. Just like no binding, you just run like in my laptop, no difference. And then I have my CPU follow memory algorithm, where the host CPU scheduler understands and scans the page table to find where is the memory of the process. So this algorithm basically scans all the processes in the system, and it can see the parent process has the memory allocated in RAM 0, and the child process has the memory allocated in RAM 1. And it drives the scheduler according to this information. So there is no binding for the CPUs. It's completely automatic. So this is the result with 1 thread. So it's basically only 2 processes. It's 2 processes, 1 thread means 2 processes. And so it's really huge. I mean, from only main policy, no, from remote and local, so the worst case and the best case, the difference is huge. It's from like 4 seconds to 8 seconds, 7 seconds, something like that. It's like a double speed if you run on the local memory for this workload. Actually, this workload, I think I've shown it in a previous slide, is mostly doing mem SMP across the memory. So it's doing huge memory access. It can do it from 1 thread, 12 thread, or 24 threads. But it's still doing something like mem CMP. And so the difference is really huge. And I didn't expect something so big. And you can see if you leave the scheduler without any binding, so if you leave the scheduler running by default, like it will run in normal cloud node without the administration fiddling with the bindings, you will get some performance which is almost as bad as the worst case. And the error in the measurement is huge. This is the percentage in the measurement. So the difference between each run, how bad was the error. And you can see here the error is huge because sometimes it will run in the right node, sometimes it will run in the wrong node. So the error is very bad. And the performance in average is also pretty bad. And for all the other cases, the error is much smaller. And with my Autonuma, I got much better performance than without Autonuma and almost as close as the 4 seconds with the static bindings. This benchmark takes 4 seconds, so it's pretty fast. And my algorithm takes a little bit to collect the information. So in the initial stage of the benchmark, the Autonuma is not driving much. And this is probably why it's not as good as here. But if you can see here, by adding threads, the benchmark takes more time. And we go from something like 12, 13 seconds in the best case. If somebody wants to have all the benchmarks and the numbers, I can provide them. Yes?
I was wondering what you meant by percent error on these slides.
It's actually printed by perf. If you use it perf minus s, perf stat, and you have to basically append the command, and it will run it many times. In this case, run it 3 times,
okay.
And it will show an error. So it's basically the measurement error. So I can't explain better than that. But if you read the perf code, you definitely see what this error means. It's out of perf. Yes?
I think I saw in your benchmark that you're always copying within the same page. And the same page is always on one node or another, correct? Copying from a remote node to a local node or vice versa. Is that what the benchmark is doing?
This benchmark is allocating 7 GB for each node and comparing the memory from 0 to 3.5, from 3.5 to 7. So it's comparing the memory, and it's accessing 7 GB of memory in each pass, and it's doing 3 passes. So it's not per page, there is no cache involvement, it's really raw memory. Otherwise, you wouldn't see this difference if it was using the cache. So this is 12 seconds, and in the worst case, we get something like 23 seconds. And the error here is pretty small for all, including the one without bindings. And in this case, the Autonuma is better than the scheduler, but not much better. And probably because we are maxing out the number of physical CPUs by running 12 threads multiplied by 2, because there are 24 threads in the host. And in this case, I'm running 24 threads as applications. So probably there is no much movement between nodes, because the current scheduler is pretty good, as I said, to keep the application sticky. And this is still a short application. I couldn't run benchmark for a month, for example, to get better statistics. I didn't have time, but this is 12 seconds. It's really pretty short. And if we do it with 24 threads, so this simulates a CPU overcommit from KVM. It's like if you're running 2 KVM virtual machines with 24 vCPUs each on a 24 host, 24 CPU host. So you get double overcommit, and there are 2 threads for each physical CPU, for each physical thread. And in this case, the Autonuma has very good error, and it also has pretty good performance. And the case here is still almost as double worse as the best case. So the remote access is still almost as double time that it takes when the NUMA bindings is optimal. So in short, I think this proof of concept shows definitely the possibility to drive the scheduler and to perform equivalently to sched affinity. Sched set affinity is the syscall you need for the bindings. So I think this is the right direction to go in terms of scheduling. And this is what I basically call CPU follow memory. So to collect information from the VM and drive the scheduler with it, just like I showed it's possible to do. But it's not enough. We also need this, we still need the sysmem policy for this benchmark to allocate the memory in the right place. Because if I don't do a memory bindings, the memory could actually be allocated a little more randomly. So we also need memory follow CPU, which should be another algorithm which runs in the background, and it interacts with the CPU follow memory. So this unfortunately didn't have to implement yet, but I think it's the right direction to go, and it's probably something we should be working on in the future in terms of NUMA and memory management. The idea of memory following CPU is simply to migrate the memory of the process to the node where the process is really running on. So I have some picture here where you can imagine two processes, process A and process B. So you can see process B has more memory allocated in node 0, and process A has more memory allocated in node 1. And we have CPU follow memory running in the scheduling of Linux. And of course, this can be a KVM. So I'm making it generic, but it can be a virtual machine here. And the CPU follow memory tends to schedule this virtual machine in the CPU 1, which belongs to node 1. And it will schedule the process B in the node 0 because there is more memory allocated there. So the idea of memory following CPU is that in the background, some other kernel thread should notice we have this process B, which has a little memory allocated in the node 1, which should be migrated to node 0 to try to converge in a single node. And to do that, however, you also need to find another process which wants to go from node 0 to node 1. And the reason is, if we don't do that, if we just blindly migrate memory from node 0, to node 1 to node 0, process B, this will grow, but it will run out of memory of the node. So if we don't migrate memory both ways, there will be a memory congestion on node 0. So we could actually migrate cache here, not necessarily the RAM from process A in the opposite direction. It's also possible to migrate cache. But of course, if we can find something else which wants to go in the opposite direction, we can improve performance for both. So it's definitely better. And we should focus on those processes which have more CPU utilization. Because if they're idle, we don't care that much if you're running a remote memory. So over time, the process B should grow in node 0, and process A should grow in node 1. And CPU follow memory should stick these two virtual machines to the right node without getting it wrong. And the nice thing is, if we use hard bindings, then we lose many CPUs. If we will be using hard bindings to make CPU, the process B stick to CPU 0 for node 0, we will basically be prevented to run in CPU 1 if there is a CPU overcommit in node 0. Maybe here there are more than one process running in node 0, but usually it's idle. If they all run at the same time and static bindings were used, we would lose the ability to use the rest of the nodes, all the other CPUs in the other nodes, to schedule these tasks which become runnable during the CPU overcommit. So I think having dynamic bindings, especially in environment like clouds, where you have a lot of migration, a lot of startups of virtual machines, and dynamic workloads, not fixed workloads like you can have in supercomputers, a dynamic approach is going to provide much better optimization of the hardware and much better performance in the long term. And right now, all the information is collected by the KNUMA-D daemon. I have this daemon scanning the memory. And in the future, this could also drive the memory follow CPU. Right now, there is also a lag of time from when the memory is first allocated and when CPU follow memory notice, because this daemon is scanning the memory. But it takes a little while to actually get the information out of the page tables and the VM. So in this time lag, we behave exactly like MPOL default. So basically, we don't have any special algorithm to use other than the current default upstream when we have no information on the task yet. But there will always be some time lag if you use KNUMA-D. We could change this to static accounting, and that would help more on the short-lived tasks. But of course, then we also slow down many allocations and many fast paths. So this is anyway an implementation problem, not so much design issue. And it's also possible to use KNUMA-D to do working set estimation. Right now I'm not doing that. So right now I'm more like checking how much memory is allocated in each node for the process. But it will be possible to clear the accessed bits for the shadow page tables for those implementations which allow to use accessed bits in the shadow page tables, or in the page tables for the host access, like when QEMU is writing to the memory directly without shadow. And doing that, we could actually detect if a virtual machine possibly has little memory allocated in one node, but it's only using that memory. So maybe there is a lot of memory allocated in the other nodes, but it's not being used. And if it's only using the memory where it's running on, then it's still an ideal scenario. And we can easily do a working set estimation with KNUMA-D, something we wouldn't be able to do with static accounting. So that's another reason why we might prefer a kernel daemon scanning the memory and driving the scheduler. Right now, we focus on anonymous memory. You know, for KVM, it's enough. Maybe this will have to change to take more into account also shared memory. And it will be definitely harder to make these decisions based on shared memory than it is for anonymous memory, which has only one user. Because, you know, there is only one process which can access that memory. So, and the last thing is about per thread information. There are complications where you have more threads than the CPUs in a NUMA node, and more memory allocated in the virtual machine than the memory you have in one NUMA node. So there was a suggestion from Peter Zastra. I hope I did the right pronunciation, I hope. And basically the idea will be to create NUMA groups, which will be dynamic or anyway virtual NUMA groups, and assign some memory range in the process to this NUMA group, and assign certain threads to this NUMA group. So basically, when you have a threaded application, you could start a thread and say, this memory will be accessed by this thread, this other memory will be accessed by this other thread. And in the QEMU case, of course, it makes life very easy to create a V topology for the guest. Because you could say the virtual CPU 0 goes to the memory from 0 to 1 gigabyte. The virtual CPU 2 goes from the memory from 1 gigabyte to 2 gigabytes. And we could actually make an easy V topology with this API. But then the application in the guests will need to still use NUMA bindings or this API to actually get the benefit from the V topology. So it's not clear what's exactly the best way to go. Personally, I think we should try first to do everything automatic. Because if we can do everything automatically, we can also avoid to change the application. That includes QEMU too. So these are called soft NUMA bindings. And I think for QEMU it will be very trivial, as I said, to describe which memory is accessed by which thread, because it's very easy to create a V-topology. But if you take a normal application which is spanning a thread, it's probably a little harder to tell to the kernel through the previous APIs of NUMA bindings that this malloc is only used by this thread, and this other malloc is only used by another thread. Basically, you have to make this call NUMA group mem for every single time you have a new allocation, if you want to take the best advantage of this soft bindings API. That's all. If you have questions.